Okay, let's talk about the new requirements on variable air volume systems. These systems are unfortunately a significant energy user, and it's important that they have requirements and that the requirements get enforced. Again, we've got our little mountain of energy diagram similar to the one we had earlier, except you'll notice there's a lot more energy being used. In the diagram, we've added a new kind of heating called reheat. In a VAV system, cold air moves throughout the building, and then in the few zones where heating is needed, that air is reheated. So the diagonal striped area that you see in here is reheat, and so we've got cold air, we're heating it back up. And this is what a typical VAV energy load looks like. So we've got significant cooling and significant heating. And I should note that this particular system doesn't quite meet the prior code, but it's often what we typically see installed, as enforcement is not always perfect. Here is the energy use of a system under the new code, and you can see first of all there is much less reheat, and that's for a couple of reasons that we'll get into based on the new requirements and the clarifications of old requirements in the existing code language, or in the new code language, excuse me. So here's what a VAV system looks like. In plan view, we've got a central air handling unit. We've got cold air moving out through the system. It moves to several VAV boxes throughout the building. In each box, and here's a cross section of a box, we take that cold air coming from the central system, and if we have a full cooling load, we open this damper up all the way and let the cold air go through. If we have a partial cooling load, we throttle back that damper so that we provide a lower volume of cold air to the space to meet the cooling load. And if we have a heating load, we reduce the cooling airflow, but we also heat it up with what's called a reheat coil, and that's where that reheat energy use comes from. So as an example of what might happen on a typical winter morning, as we're warming up the building, we might have part of the building that requires that cold air, say 55-degree cold air in the server room in the center of the building. At the same time, the perimeter of the building, because of the envelope, is losing heat to the outside and still trying to warm up from being cool overnight, and we're reheating that perimeter area by taking the cool air that we need for the server room and heating it up to provide 85 degrees to try and warm these perimeter spaces up. So the reheat is required in those perimeter red spaces. In another example, moving more into the summer when it's not quite so cold outside, again in the early morning we might have a situation where the entire east side has the sun blazing in through the windows, and it requires 55-degree air in order to stay cool. The north side of the building might still require heat since it's warming up. Maybe it was a cool night, and then we've got less stringent heat requirements on the other perimeters of the building, and kind of a moderate temperature below set point just to moderately cool the interior of the building. So notice that we've got a difference in requirements in different parts of the building, and hence the system is going to have to respond to each of those areas. Now there's a strategy called supply air temperature reset that can save significant energy in a VAV system. In the old code there was required a 25% reset. In the new code it's 35%, and that percentage is between the design supply air temperature at the central fan and the room set point, typically 70 or 75 degrees, the comfort set point temperature that needs to be met. So a 35-degree reset might mean a 7-degree reset requirement. So let's think again in detail about a VAV system. we've got our central fan, we've got our economizer that we talked about previously. We're now supplying cold air to the building, either cold air that's from the economizer or has been cooled with mechanical cooling, usually from the chiller. That supply air comes down to the zones, and each zone, the volume of air is adjusted based on what is needed for that particular zone. In addition, if one of these zones needs heat, we're going to crank on the heat to meet that zone's load. So let's talk in more detail, take a closer look at what's going on. So we've got this cool supply air coming in. The trick is, how cool does that air really need to be? If I can meet the requirements of all of these zones with 65-degree air, then why should I cool it down to 55 degrees? I'll save cooling energy first of all. And then when I get to that one zone over here on the end that might need reheat, if I have warmer air coming into that zone, I'm going to have less of a heating need to meet the requirements of that zone.